Okay, let's start today's class. Actually, recently we talked about Fourier series. Actually, this part is the most difficult part in this course. So yeah, because it's quite abstract to understand, because you need to imagine to analyze this signal in a frequency domain, but that domain is now is now the common domain, you like the time domain, it's very direct, but the frequency domain is abstract to imagine. So I will try my best to make it clear. And if you have any questions, just let me know. I will make the speed lower to tell you every details. And if you have any questions, just let me know. Okay. Yeah. Today we will continue to talk about, first we will review the harmonically related complex exponential signals and the sinusoidal signals, and then try to review the definition of a Fourier series representation for periodic, continuous time signals. And if we have time, we will try to it's a little lower. And then we try to, if we have enough time, we will try to study 3 cases of typical Fourier series computation problems. Actually, we can sum all of Fourier series computation problems into 3 different types. Yeah. Okay, we will talk, firstly, let's review the harmonic Fourier series terms for periodic signals representation. Actually, if we have periodic signals like xt equal xt minus plus capital T, actually this is a general definition for the periodic signal. Am I right? Yeah, if you have a signal xt, and if xt equal xt plus capital T, and then this must be a periodic signal. That makes sense to you? And what's the period? Yeah, capital T. And what's the fundamental frequency? Yeah, 2 pi over T. Yeah, you need to remember that. Then, this is a harmonic related complex exponential. Yeah, this is just why we call it harmonically related complex exponential. Do you know? Yeah, because you can see as a key change, and it is just because you can see here the omega naught. What's omega naught? Is fundamental frequency. I'm right. If I give you a periodic signal, the fundamental frequency is fixed. I'm right. That makes sense to you. And E is fixed. I'm right. E is just a 2.7 blah blah blah, and G is just the complex symbol. It will not change. I'm right. So the omega naught will not change. I'm right. T, only the T is changed. T is time. I'm right. It is just from infinity to the negative infinity to the positive infinity. You can represent it the signal from positive, and the key is just from it will change by the different integer, 0, 1, 2, 3, -1, -2, -3. And this one actually is just kind of harmonically related. Yeah. That makes sense to you? Yeah, actually, do you remember the 3D vector representation? Yeah, we know this signal actually, if you have a signal and the fundamental frequency is equal to this one, actually you can represent this signal using the harmonically related complex exponential. Yeah, we have talked about in last class. Am I right? Yeah, actually this harmonically related complex potential. Do you remember the image? Yeah, let's review all these things firstly. Yeah. Yeah, this is what we have already talked about in NAS class and the NAS class, am I right? Actually, you can see this is just the as the key is different, am I right? And then, for example, like the EG, I want to tell you the EG, if it is 0, if k is 0, what's the value for that? 1, am I right? So it's the 5 kt, like it's just 1. If it is a negative 1, it is just k, there is no omega now t, and the EG t, q omega now, 2 omega t, and here is sorry, EG omega now t, and EG q omega now t, and blah 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 blah. Does that make sense to you? Am I right? Yeah. So actually, you can see if the omega now is fixed, for example, like t equal 2, am I right? And the omega now, what's omega now? Pi. That makes sense to you? Yeah. So this is just a p negative g pi t, am I right? This is what's this? This is cosine pi t plus g sin pi t, am I right? And the sin pi t equal what? Oh, no. Sin pi t, you cannot like, yeah. The cosine pi t, it's just like a cosine similar like this, am I right? And this sin pi t is just like a plus d. You can represent this image using some like for example, the signal is just like this, am I right? That makes sense to you? Am I right? Yeah. And then you can see this is one. One is what? One is just a line. Am I right? And what's this is this is negative. This is negative, and this is positive. It's just the similar one, but just flip. Am I right? Like, yeah, similar like that. And you just add all those together and can get the xt. Am I right? We have already talked about that. Actually, do you know like a different component? This one. Actually, they have relationship. You know what's a relationship? Yeah, you know, like we use this one, am I right? This is 3D vector, am I right? We can like a project into different like axes, and we know like the for here the harmonic related complex exponential is just a similar like a different axes, am I right? But here there is only 3, am I right? But here how many? You know how many? Infinite, like theoretically infinite, but sometimes it's limited because for specific signals, am I right? Yeah, which means for this one, it's just like it's not only 3, it's maybe 4 dimension, like 6 dimension, 8 dimension, am I right? But there is one, all those dimension, all those complex exponential has a relationship. Do you know why? Do you know what's the relationship based on this one? Actually, you can see the harmonic related complex exponentials, the different atom, they will be for the geometric. If you analyze those in geometric, it's all alternative with each other, like a like a perpendilar. Am I right? Perpendicular with each other. Yeah. Perpendicular with each other. Yeah, they have this question. They have this relationship. Actually, the harmonic related complex exponential and harmonically related sinusoidal signal. It's same thing because you can transfer this one to this one. Yeah. So it's the same thing. Yeah. So when I talk about like the harmonic related complex exponentials, you need to think about like, oh, there are different atoms. Am I right? You can you can like try to represent the original signals with different like companies. Am I right? Those companies actually it's just a perpendicular with each other. Yeah, in the geometric form. Yeah, you need to think about that. Okay, yeah, this I want to review this. Why? Because it's very similar to represent a 3D vector. This is the analysis form, and this is the analysis form. For the Fourier series, it also has those two different forms. And this is A, like this is A, this is B, this is C. And actually, we know like this is the dot product. Am I right? Do you know what is dot product? Do you know? I think you learned this in calculus, am I right? Yeah, but actually, I thought you should know that, but maybe you will forget that because the calculus maybe is first semester, am I right? Yeah, first. Oh, yeah, maybe you. I want to give you a reminder. Like, yeah, dot product is if you this is a vector, this is a vector. The dot product, which means you need to multiply them together and add them together. Yeah, this is dot product. Do you remember? Yeah, that's the reason why. Do you know, like this is this for a Fourier series, this is signal synthesis. We can use this to the signal synthesis, am I right? Like it's very similar to here. This is a vector synthesis. Yeah, different component X, Y, Z. And ABC is just the like coefficient, am I right? And here the A key is just coefficient. The E G key omega t omega naught t as a key different. It's just different like axis. That makes sense to you? And why I want to this is and for the coefficient we know like the A key is just the original signal. That P is just a similar like original signal. Dot product with a different axis. Am I right? Here. Okay, sorry. Yeah, the xt is just similar like the p. Here. This is very important. It's different, similar like p, am I right? That makes sense to you? And the dot product with EGK omega now. EGK omega is just similar like a different axis, am I right? Yeah, that's the reason. This is complex dot product. Why it equals this one? Just because this equation. Yeah, because it's just like multiple together and add together. Yeah. Yeah, you can see the ft is similar like p, right? The p is just the original signal. And this EG k omega naught t is just like a different axis. And what's the dot product? It's just multiple and add. Did you? Yeah, that's the reason why we just use like the integral to represent the coefficient here. Yeah, I want to explain this for you. Any questions so far? Okay, and then yeah, we can easily write this one to this one because replace the omega naught with 2 pi over t. Okay, there is one thing you need to notice. When you calculate it, you can see this is gk omega naught, right? But here, this is g negative gk omega naught t. Yeah, you need to add a negative here. Yeah, did you notice? Yeah, did you notice the difference? Yeah, that's the complex dot product, the definition. You need to check that. Yeah. So when you calculate, you need to pay attention to this one. Okay. And then the fs coefficients are the inner products or the dot products between the signal and the harmonic related complex exponentials. Yeah. Let me see. Okay. And then this is what we talk about. Yeah. And for the fs coefficients, yeah, we know like this is the harmonic related complex exponentials. And as this is for example, the omega naught is fixed. This is EG omega naught t, and this is 2 omega naught t because it will if your like fundamental frequency is omega naught and your t is t naught, and then if your like a frequency fundamental frequency become 2 omega naught, which means your t will become what? Half. Am I right? You can see your t will become like a, yeah, you can see this is t, and your t will become the original half. Am I right? And similar, if your 3, it will be third and the fourth. Yeah, that makes sense to you? Yeah. Then, yeah, the 5 is fifth. And this is like, what's the name for this equation? Signal analysis or synthesis? Yeah, synthesis. Yeah, if it is if you want to represent the original signal, it is synthesis. If you want to represent the like coefficient, it is analysis. Actually, it's similar with this one. If you want to represent the different like coefficient thing, yeah, it is analysis. If you want to represent the whole total, like yeah, it's synthesis. Okay, yeah. Since this is you want to represent the original signal, so it is signal synthesis, and then equal this one. We know that, and this is the coefficient. And we know here, actually, since there have this atom, yeah, we know like the coefficient, this AK is a complex number, am I right? Yeah, for a complex number, we can write, yeah, actually we can write any complex number in this form. For example, you have a complex number, and this is R, E, G, like A, this one. Actually, you can represent any constant number. This is magnitude, and this is like angle. Yeah, actually, this is like the definition for the complex number. If you learn, have you ever learned complex number before? Yeah, you should know that. So that's the reason why we can write this equation here. This is the magnitude. This is the phase shift, like phase angle. Yeah. Yeah, actually, this is the magnitude of each harmonics, and this is the phase shift of each harmonics. Actually, we talk about the AK. It's just related to magnitude and the phase angle of phase shift. Am I right? Yeah, you can see here. We have different like harmonic related complex like exponentials. Am I right? We have if we change the key, am I right? We have different like but if you want to know the original one, you need the amplitude and the phase shift. Yeah, so the A key will give you. Yeah, okay, and then from the original equation, we know like the AP you can the AP equal this one, right? So you can just multiple with the like different like companies, and then you can see actually it's just like this one. What does this one mean? Phase shift, am I right? Yeah, and this one is just magnitude. That makes sense to you? Yeah. Okay. Okay, let's try to talk about the geometric interpretation of Fourier series fs. Yeah, actually, this is very similar to what I have already talked about just now. You can see, given a periodic signals, periodic signals, and the fundamental frequency you will know, am I right? And then this is actually, when we talk about it, this is similar like the geometric thing, am I right? Yeah, so we know like the this is different components, am I right? Different aspects as a key, different, am I right? And for example, we call it harmonic related complex exponentials. For example, we have 5 different axes, am I right? And when the key from -2 to 2, and then different like contexts. If we want to represent the original signal, right, we need to know the A key, the coefficient. That makes sense to you. If we know this A, this B, this C, then we have already know the X, Y, Z, we have found, right? So we are easily to get P. That makes sense to you to get the signal, right? Yeah, so which means the AK, if we can get that, we can use this equation. What's the name for this equation? Signal analysis, right? And then you can use, then after you get the AK, you can use it to get use the synthesis to get the original signals. That makes sense to you? Yeah, actually, those can, like from A to B, from B to A, like that. Yeah. Okay, this is an example. We talk about that. Actually, we haven't finished the example in last class. This is the original signals. Yeah, this is the signal ST. Actually, this ST, you can, if you draw it, it's just similar like this. And then I give you the A0, A1, which if this is A0, which means K equals 0. If it's 1, which means K equals 1. -1, K equals -1, the similar thing, am I right? And so what equation we can use if we want to firstly, let's try to very important thing I forgot to mention. For those questions, if I give you a signal, the first thing you need to find the fundamental frequency. Yeah, because it's decided like the following equations. Yeah, that makes sense to you? Yeah. Okay. For this one, what is the fundamental frequency? Yeah. Okay. For example, this one, what is for this equation, what is fundamental frequency? Omega now, am I right? Yeah, omega now, obvious, am I right? So compare this one with this one. 2 pi, yeah, that makes sense to you? Yeah. So the fundamental frequency is just when the k equal 1 is 2 pi. And the periodic period is just 2 pi over omega naught equal 1. Am I right? Yeah, this is easy. So then you can write your equation like this. Yeah, you can see. Let me write it down. Yeah. When let's try to x t equal, you can see it is multiple, so which means a -2 e g -2 pi 2 pi, yeah, 2 pi t, am I right? Like this, am I right? That linear -1 e g 1 2 pi t, and plus a 0 e g 0 2 pi e, plus a1 e g 1 2 pi t, plus a2 e g 2 pi t, right? That makes sense to you? Yeah. Here we know like the a -2 and the a2 is same number. Am I right? It is what? Is what? Oh, okay. Here also has 3. I forgot that. But it's a similar thing. Am I right? So, like if a2 and a negative, a3 and -3, it has the same value, am I right? So we just put it together. 1/3. This is e g. Yeah, since like k is 3 multiple 2 pi, am I right? This is 6 pi, and this is -6 pi. It means -3, am I right? And similar, this is 2 when k equal 2, -2. When k equal 1, -1, and this is k equal 0. Because k equals 0, what's the value? Here it is 1, am I right? Because this is 1, am I right? A0 equal 1. 1 multiple 1 is equal 1. So we can get this one. That makes sense to you? Any questions so far? Yeah, you can see here, this is just 1, and this is just like 1/4, and this is 1/2, 1/3, am I right? And then you can see, actually, what's the equation? What's the equation for this? What's the name for this equation? Transfer the sinusoidal to the exponential complex exponential transfer the complex exponential Euler equation. You just remember the Euler equation is very important in this class. Yeah, it can be transferred with each other. Am I right? Yeah, so you can see, compare this one and this one. So did you notice it's just a similar? Did you notice from this one to this one? Am I right? It's very similar. Am I right? Yeah, so which means you can transfer this to cosine. Am I right? Convert this to cosine. So you can get this one. That makes sense to you? Yeah. Why? Here is 1/4. Here is 1/2. Because there is a 2. You need to consider that. Am I right? Yeah, you need to, if you want to get this part, you just put a 2 in this side. That makes sense to you? So you can get this one. Am I right? So, which means this periodic signals can be like a form, can be generated from this one, and this one. Those sinusoidal signals. That makes sense to you? Yeah. Okay, let's try to continue. Did you see any phase shift in those sinusoidal shifts signals? What? Did you see any shift? Any phase shift? Did you? Like if we talk about that. Yeah, this is like this is AK, am I right? And this is your AK, am I right? So did you see any shift for now? If you have shift, which means you have this plus something, am I right? Did you? No, am I right? Yeah, that's right. There is no like a phase shift like in those sinusoidal signals. But why? Do you know why? You can see actually you can observe it from that just from the AK. You can see if your AK has a phase shift, which means this is the magnitude, this is a phase shift, which means you have involved imagine part. If your AK is just a real number, which means it's just like it's just related to the magnitude. If your AK has a imagined part, then which means your like these companies will have phase shift. Yeah, because you will have this part. That makes sense to you? Any question? Okay. Yeah. Okay, let's try to yeah. You can see f's coefficients are real without an angle term, which means if your coefficients are real, which means there is no phase shift if it has the imagined part. Imaginary, imaginary. Yeah, I think imaginary part. Yeah. Okay, let's continue to observe this one. Yeah, actually, this is X signal when the signal equal 1. Am I right? Yeah, this is the signal when the for this part. And this is the signals for this part. And this is the signals for this part. Am I right? Yeah, we know like the original is just similar like this. It's not similar. It's this is the original one. So I just want to show you. Yeah, the first part and the second part, if you add them together, what will happen? If you just add 1 to this signal, add 1 to this signal, what does that mean? Shift up like this, am I right? Yeah, all the value will shift, will like add 1. That makes sense to you? Yeah, this one is, but that one, if you add those one and this one, you can get this one. If you add this one and this one, you can get this one. Yeah, this is just the same with this. Yeah, this is how how to get your signals. Yeah, that makes sense to you? Okay. Yeah. Okay, recall what is fundamental period frequency. What is let's try to recall what is a fundamental frequency. Yeah. omega now, am I right? Yeah. What's omega now? We just talk about 2k, am I right? Yeah. So the t is 1, am I right? So you can see here. This is t, am I right? Yeah. If you observe from here to here, it's just a 1. Yeah. Okay. Yeah, you can see here. This is the fundamental frequency 2 pi. Yeah. So okay. And let's review the polar representation. Have you ever touched this before? No? Yeah, we know like when you want to represent a number, just a number, in 3D, like not 2D, like a 2D, have 2D information. We want to represent a complex number. Yeah, like one is x, the other is y, right? And then like your number is. Yeah, this is your complex number, am I right? So you can represent any constant number in this axis, am I right? For example, here is 1, here is 1, am I right? This number is just 1 plus g, am I right? That makes sense to you? Yeah. Except, have you ever touched this before? Yeah, I think, yeah. And for the 2, and for this is just like a 2 plus g, right? And different things. And here, you can present any complex number in this using this axis, am I right? But this is just what we represent in a normal way. This one, the polar representation, which means you not only represent it like that. This is just your x, and this is not y. This is your g, which means, and here it's just a different angle. Yeah, and then you can represent your specific alpha, specific complex number, the cosine phi plus I sin phi. Yeah, which means you can represent the complex number in this circle using this equation. Different phi, and you can see you can have different complex number. Am I right? If you can represent any complex number using this method, how can you do that? For example, here, this one. How can you represent this one? How?
Like from the left one.
Uh-huh.
And say
Yeah, which means here the distance is 1, right? Here the distance also 1, right? This is 1, this is 1, right? But if you want to represent this equation here, which means you need to know this distance and this distance. That makes sense to you? Which means, for example, this is A, this is B, all right? Which means you just try to multiple coefficient here. That makes sense to you? Yeah, and then you can represent any complex number using this method. That makes sense to you? Yeah. Any questions so far? Okay. Yeah, this is a polar representation. So which means if we want to represent a complex number, there are 2 different ways. One is the normal way, x, y, z, and x, y. Yeah, x plus yg, right? I think this is a common representation. But there is the other one, like cosine phi plus I sin phi. If you want to represent different number, what you need to do is just actually it's very similar to the EK. It's just multiple amplitude, like a magnitude. That makes sense to you? Yeah. Which means here, just similar, for example, you want this one, and then this is your, and you get this one and this one. This is your cosine. This distance, am I right? And this is the distance. Am I right? That makes sense to you? Any questions so far? Okay. Yeah. Okay, let's try to review the other questions. CT periodic signal is real varied and have a fundamental period T equal omega T equal 8. What's the fundamental frequency? Yeah, the first thing always find the fundamental frequency. I give you the fundamental period is 8. I think this one is easy, am I right? 2 pi over T, am I right? What's that? Oh yeah, pi over 4. Yeah. The non-zero Fs coefficient A1 equal A negative 1 equal 2, A2 A3 equal A negative 3 complement equal 4G represent XT in terms of, yeah, this is just like a cosine thing, which means you need to use Euler equation. Finally, you need to use Euler equation to convert the complex exponentials to sinusoidal signals. Okay, let's review. Yeah, we know like the omega equal 2 pi over T, and A1 equal A negative 1, 2, A3 equal this one, and yeah, you know why this one? So why not this one? You know? Yeah, because you can see we just review this one. Am I right? Which means if you want to represent this one, it's cosine phi plus I sin phi. This is different signal, and this one 4G. Yeah, this is just like a, which means let me write it down. Yeah. E phi equal cosine phi plus G sin phi. Am I right? Yeah, this is the Euler cosine phi. G and I is a similar thing. When you represent the complex number, do you usually use I or G? G, am I right? Yeah, but also I can work. Yeah, sometimes some document have, but it's same thing. Yeah. So, which means here, yeah, here this is 4G, am I right? Which means here you have 4G, am I right? And you should have sin phi, but obvious here phi sin phi equal what? 1, am I right? That makes sense to you? Yeah. So which means like your sin phi equal 1, your phi equal what? Pi over 2, am I right? Yeah, smallest. That makes sense to you? Which means when you're like phi equal 2 over 5, this one 0. That makes sense to you? Any question? Yeah, so this is E J phi, just E J 2 pi over 2 over 5. And here you have a coefficient, you need to multiply it. That makes sense to you? Yeah. That's the reason why it's equal that one. Am I right? Yeah.
Because we're just A, so that means cosine has to go to 0.
Yeah. This one must 0, am I right? This one must 1, am I right? And then you just get the smallest, yeah, you can have this one. That makes sense to you? Okay. And then the A negative equal negative 4G. Do you know this star symbol? You don't know? You don't know? Okay. This star symbol, which means yeah, it's just like a negative for like a 4G. Yeah, which means it's just for the complex number. When you have a complex number like A plus BG, and if this is your complex number, and then X, this symbol is equal B, G. Have you ever heard this before?
It's the empty.
Yeah. Have you ever? Yeah, because here is just 0, am I right? Yeah. So I think you must know this, but you just forgot that. Yeah. Okay. Then this is for what's the value for this one? Yeah, -4. Yeah, like a 4. Yeah. Does it make sense here? Yeah. Okay. Any question? No. Okay. And then you can see we know like the omega naught, we know A1, we can use what equation? We want to calculate the signal. So the synthesis. Yeah, synthesis, am I right? Yeah, this one. So yeah, omega naught equal pi over 4, am I right? Yeah, you know that. So which means we have this one. Yeah, this is just from one more thing. If I give you this one. Oh, sorry, I think yeah. I give you, which means here the non-zero fs coefficient, which means the other coefficient will be 0. This is just only the non-zero coefficient, which means from when t equal 1, -1, when t equal 1, when t equal -3, when t equals 3, it has value. Otherwise, there is no value. That makes sense to you? Yeah. Okay. Then from this one, you can get this. That makes sense to you? Yeah, because you can see this one and this one. You put the 2 out, and then this one and this one is just like you can use the Euler equation. Euler equation here. That makes sense to you? Yeah, and then you can easily get this thing. And for this part, for this one, yeah, you can see this is just the like how can you write this to the cosine? How?
Just take everything about them.
Yeah? Yeah, actually, I think this is just similar with this one, but you need to pay attention why I put it out, because the omega now is now just a one atom. It's just this is just your omega now. That makes sense to you? Yeah, then you use the same equation. That makes sense to you? Yeah. So you don't think, oh, this is very complicated. Why? Here is 2 atoms plus. So can I use this one? Yeah, just consider this is just a one yeah, it's 2 atoms, but you just consider it is omega now. Omega. That makes sense to you? Yeah. Okay, any question? So then you just represent the original signal with the sinusoidal form. That makes sense to you? Yeah, okay. And then actually you can easily to draw this one and draw this one and combine them together, add them together, represent the original signal. Okay, let's try to review. Yeah, this one is just this one. It's the same thing. Yeah. That makes sense to you? Yeah, because you just put omega naught into this, like cosine pi over 4. This is you can use any program to draw it. Yeah. Okay. And let's try to where does this redshift come from? You know?
A or 3.
Yeah, because the A3 and A-3, you can see this is only has imaginary part, so they will involve some redshift. Okay, let me ask a question. If A3 and A-3 equal 2 plus 4G, will there be a redshift? Are you sure? Yes, it will. How can I see? If there is a imaginary part involved, there must be a phase shift. imaginary, the real part is just related to the magnitude, the magnitude thing. Yeah, but if there is, yeah, you can see this is, sorry, here, this is magnitude, am I right? Because there is a four, because it's just like has the four. Yeah, this is EK, am I right? Yeah, this one, am I right? But if there is an imaginary part, there must be a phase shift. That makes sense to you? Yeah, just remember that. Okay, let's try to review this one. Give a CT periodic signal, this one. Determine the fundamental frequency and the Fourier series. Okay, you have this one. Let you determine the fundamental frequency and FS coefficient. What equation you will use? Yeah, analysis. Yeah. Then we know. Oh, sorry. What's the periodic signal? What's the fundamental frequency? What's the fundamental frequency? You can see, actually, you will be confused. There is two, there is a 3/2. Sorry, I have already showed it to you. There is a 2 pi over 3, am I right? And there is a 2 pi over 3. There is 5 pi over 3, am I right? But if you observe those two, actually those two have relationship. Did you notice that? Actually, yeah, did you notice that? Yeah, this one equal what? Yeah, it's just like a 2 pi plus 3 pi, am I right? It is 2 pi over 3 plus 1 plus pi, am I right? It's just a pi like difference. So this one, those two are similar. The fundamental frequency, you need to focus on 2 pi over 3. That makes sense to you? Yeah. Huh? Lower, yeah, because it's just a pi difference, am I right? Yeah. So, which means your omega now should, sorry, I think I just make a, yeah, this one, let's step by step. Yeah, this is 2 pi over 3, am I right? Which means your t is 2 pi over omega 1 equals 3, am I right? And this one is, yeah, we should calculate the time. Yeah, this is 6 over 5, am I right? Yeah, and then you just calculate the least common multiply. Yeah, it's a similar thing. Yeah, it's this one we have already learned in the chapter 1. Yeah, actually, yeah, this is the t equal 6, and the 2 pi over 2 pi over 6 is pi over 3, right? Yeah, that makes sense to you? Yeah, okay. Which means actually what I want to what I just talk about is just a very quick, very fast method, because you can see this is like a 2 pi over 3. Actually, this is 5 pi over 3. The fundamental is just 1 over 3, am I right? Am I right? So which means the omega now should 1 over 3, because this is just a multiple 2. This is just a multiple 5, am I right? So like a 1 over 3 pi, 2 pi over 1 over 3 pi, it's just a 6. That makes sense to you? Yeah. Okay, this is the other way, but to make this clear, you should use this method, because this method will you will now make a mistake. Yeah. Okay. And then over like omega now equal 2 pi over t is pi over 3. Yeah, but you can see, you can observe from this one and this one. That makes sense to you? Yeah. Okay. And then like by inspection, can you tell the fundamental frequency? It's just like what I just talked about. If you can see, you over this is pi over 3 multiple 2, this is pi over 3 multiple 5, which means the fundamental frequency should be pi over 3. That makes sense to you? Yeah. That makes sense to you? Huh?
Is it just multiples of power 3?
Power 3? No, yeah, it's multiple pi over 3. Yeah. Which means that, this is just the integer multiple the same thing, the same atom. Yeah, but you can see sometimes it's complicated. So you'd better use this method. That makes sense to you? Yeah, okay. And then let's try to find the fx coefficient. We know like this one, am I right? And then we have Euler equation. So, oh yeah, we have already. Maybe we can continue like next class. Okay, yeah, and continue this these things. Yeah, we will like spend more time on those things because it's quite complicated. Yeah, any questions so far? Okay.